So the next question is, how do we really go and find the vector w that maximizes the margin? So the question is, how do we precisely compute the margin? So now what we will learn is where the name of the support vector machines really comes from. And our idea, right, so far was to find a separating line that maximizes the margin. And if we think about it, we can draw the following picture, right? We have our, let's say, negative training examples, our minuses on the top, and we have our pluses on the bottom. And what we want to do is we want to find a line that maximizes the distance of the closest point to that line. And the way this line is simply defined, it's defined by a few points that are closest to it, right? What this means is that we could ignore all other data points if we would have these three circle data points, because they already uniquely define the line. And these three circle data points, they are called support vectors, right? The line, the separating hyperplane, is uniquely defined in this case by three supporting support vectors. So now the question will be, how do we go find the support vectors and how do we find the line? Generally, if our data is kind of not degenerate, then if we are in d-dimensional space, we need d+1 support vectors to define such line. While we have already talked that gamma corresponds to the margin, basically corresponds to the distance of the point from the hyperplane, here is a problem. The problem is, imagine the following. Imagine that I have a data point x, I multiply it with w, add this b, multiply with the class, and I call this gamma, which is the margin. So now imagine that I take my vector w, but make it twice as long. So I just kind of take twice the w plus x plus twice b times y. What this gives me now is twice as big margin. So it seems, based on this simple calculation, is that the longer we make w, kind of the bigger the w is, the bigger our margin will be. And this basically means that there is kind of very hard to optimize this, because we can just make w as large as possible, and the margins will also get as large as possible. So we are not doing anything useful. So the solution to this problem is that we need to work not with w, but with a normalized version of w, in a sense that we want to think of w as a vector that has length of 1. So what this means now is that we will change the definition of margin slightly. We are still taking wx plus b times y, but now we are working with a normalized version of w. So we are also dividing by the length, by the Euclidean length of w, in a sense. And the Euclidean length is simply the sum over all the coordinates, taking the square of those coordinates and then the square root of the sum. So now, this is the first thing we do, is right, the first change is that we will be working with a normalized version of w. And this changes the notion of the margin a bit. The other thing that will also work is not, now that we will require support vectors x, these are these three circled data points, to be defined by the line w times x plus b equals plus or minus 1. Right? So going back to my picture, our decision boundary is wx plus b equals 0. So now the left support vectors are wx plus b equals minus 1, and the right support vectors are wx plus b equals plus 1. Right? So we are in some sense requiring that this here is of unit 1. So now the question is, how can we put all this together and find the optimization problem that will allow us to maximize the margin? So the goal is still to maximize the margin. Now the question is, what is the relationship between data point x1, which kind of is here on the margin on the other side, and data point x2, which is our red data point here? What do we know is the following. We know that x1, the value of the data point here, is simply x2 plus twice the margin times the normalized version of the vector w, right? So if I have my vector w, then what's the distance between x and y? I simply have to take this vector w and multiply it by twice the margin, because there's one unit of margin gamma here and another unit of margin gamma at the bottom. So that's the first kind of equation that we know. The second equation that we know is based on our assumption on the previous slide, that the left side of the margin is defined by wx plus b equals minus 1, while the right-hand side of the margin is, or the bottom of, on the other side of the decision boundary, is defined by wx plus b equals plus 1. So I can also go and write out both of these constraints. So what I can do now is I can take this system of equations and try to solve it, right? So I take the first equation and I enter and I substitute x1 from the top equation to obtain the next one. Now if I go multiply this through, I get that w times x2 plus b equals twice gamma, and then I have w times w equals plus 1. What we notice now is that I can use the last equation and notice that wx2 plus b equals minus 1. That's the first thing we notice. And this already now solves the whole equation for gamma, right? What we see is that we can solve now for gamma. So we see that gamma equals the length of w times the w dot product with itself. What do we note now is that w times the dot product with itself, that is simply the square of the length of w. So the square root of the length divided by the square of the length is just 1 over the length. So what we arrived to is that gamma, our margin, is 1 over the length of w. So to summarize what we know so far, we started with the first optimization problem that simply says we want to find w such that the margin is maximized. And what is the margin? The margin is the distance of that all the data points that we have the classification or the confidence greater than gamma. So that was our initial optimization problem. What we noted then, that this initial optimization problem can trivially be solved by making w as large as possible or arbitrarily large. So there is nothing kind of useful in solving this problem. So what we did then was we said, okay, let's normalize our margin by the length of w. So we said maximizing the margin gamma is the same as maximizing 1 over the length of w, which is kind of the same or equivalent to minimizing the length of w, which is the same as minimizing 1/2 times the length of w squared. And just for some technical reasons, at the end, our goal will be to minimize the 1/2 the length of w squared. So now that we have transformed kind of maximization of gamma to the minimization of the length of w, we can now write down the support vector machines margin maximization optimization problem. So our goal right now is the following, and equivalent to the optimization above modulo the problems that we resolved. We want to minimize the length of w, so we want to find w such that it has the smallest length, while our classification margin, our confidence in classification of all the training data points is greater than 1. And this optimization problem that I wrote down here is called SVM, or support vector machine with hard constraints.